our goal today is to simply introduce the Research Center, the Center for Unmanned Aerial Systems, that's based here at Brigham Young University. And we have a sister university who helps and also founded the center. That's the University of Colorado at Boulder. So the way our presentation will go today, I will turn the time over to Dr. McLean, and he will introduce the center and show a little bit of the research specifically related to the UAV platforms that we perform here at the Research Center. And then he will turn the time over to me and to Dr. Hedengren, and John and I will talk a little bit about some of the research that we are trying to initiate to look at infrastructure monitoring and applying UAVs to improving the way that we can monitor infrastructure and detect significant anomalies. So with that, I will turn the time over to Tim.
Sounds great. Thank you, Kevin. Well, I appreciate the opportunity to speak to you today about our center and give you a bit of an introduction. I'm first going to give you an overview of the Unmanned Aircraft Systems research at BYU, and then I will shift gears a bit and talk about our center that's been established. The center is part of the National Science Foundation Industry University Cooperative Research Centers program. I'll explain that program to you. I'll give you an update on the status of our center and also talk a bit about some of the research projects, and then we'll talk together about opportunities for collaboration, and I'll turn the time over to Kevin towards the end of that when we're talking about the research projects. Just to give you a bit of background, at BYU we've been working on unmanned aircraft systems for about 14 years. We got our start in 1999. I was a visiting scientist at the Air Force Research Laboratories in Dayton, Ohio, and started working there on cooperative control. The little graphic you see at the upper left shows a simulation of unmanned aircraft being used to monitor the growth of a forest fire. And as the fire changes and grows, the UAVs track the perimeter of the forest fire. The initial problems that we worked on were cooperative control problems, and it didn't take us long to learn that if you were going to have UAVs cooperating with one another, that you needed to have the capability to plan the paths of the UAVs to determine where they should go and when they should be there. And so we started working on path planning and trajectory generation. And during that work, we decided that we wanted to do some experimental flight testing to demonstrate the effectiveness of our approaches. And we developed an autopilot for unmanned aircraft. And you can see a picture of that autopilot in the bottom center of the screen. That research that was funded by the Air Force to develop the autopilot was very successful and resulted in a commercial product that has done very well. And having that ability to be involved in the design of the autopilot and the control of the aircraft at really all levels, from the high-level guidance and control and planning, mission planning, down to the very lowest levels where we're controlling the dynamics of the aircraft itself, has been very beneficial in terms of what we're able to do in terms of research. I'll also mention we've done some what we call image-directed control or vision-based guidance of aircraft, and I'll talk a bit about that as well. This next slide just shows across the bottom a number of the platforms that we've worked with. You can see that we've worked with very small aircraft. The aircraft on the far left is called the BATCAM aircraft. It's an Air Force vehicle and has a wingspan of just over half a meter. As you go along the bottom, you can see some foam flying wing aircraft. The second from the left, and we've used those aircraft a lot simply because they're very tough and very durable. And in the course of doing research, you need an aircraft that can handle rough landings and even unanticipated crash landings as we're exploring new things. The vehicle in the center is a vertical takeoff aircraft. It's a tail sitter. It takes off vertically and then can transition to horizontal flight. So it can hover and land in a confined space like a helicopter, but it can also fly very efficiently like a traditional fixed-wing aircraft. And then further to the right, you can see a quadrotor aircraft, which we've used those most recently quite a bit, and then a traditional fixed-wing aircraft with a fuselage and a wing. Some of the research technologies that we've been involved with are listed on this page. I mentioned that we've had some commercial technology transition success. The autopilot and some of the other technology we've developed was transitioned to Procerus technologies in 2004 and in subsequent years. And then in 2004, Procerus Technologies was acquired by Lockheed Martin. Our guiding objective for our research is to develop enhanced autonomous capabilities for small unmanned aircraft. We have developed some of our own sensors here at BYU. We use a lot of commercial off-the-shelf sensors as well. But really our primary focus is on the development of autonomous capabilities in terms of the autonomy algorithms, and developing algorithms and approaches that are suitable for the computational approaches that we have available to us. On small aircraft, we don't have typically large computational resources on board the aircraft. And so it's important that the algorithms be very efficient and designed so that they can suitably exploit the resources that we do have on board the aircraft. Our main goal is to approximate the capabilities of large unmanned aircraft, such as a Global Hawk or a Predator type of aircraft, and to do that with a smaller, lower-cost unmanned aircraft platform. So that's really what guides a lot of our research efforts here at BYU. If you have any questions, please don't hesitate to speak up, and I'll do what I can to address them. What I thought I would do is just give you a brief overview of some of the different technologies that we've developed. This first example is an example of localizing a target on the ground. So this could be done to localize a moving target, or it could be done to localize a specific object on the ground. In the graph at the lower left, you can see that this is an example of some data that we've gathered. The blue dots indicate the location of the aircraft. The red dots indicate the instantaneous estimates of the target estimation, and then the black dots indicate the averaged or filtered estimate of the target. And you can see that our estimation errors are on the order of 2 meters here in terms of the target position on the ground. The basic idea is if you know the attitude of the aircraft and you know the location of the aircraft, as well as where an object of interest is in the image frame of the aircraft, then with that information you can compute the location of the target on the ground. The next slide, hopefully you're seeing some video playing. This shows some of the capability that we've developed with the autonomous target tracking. This is an unmanned aircraft, a fixed-wing aircraft that's flying over the top of a moving target. In this case, it's a vehicle. And the operator clicks on the target, and the software automatically guides the aircraft to hover over the target, to maintain the camera focused on the target. And then you can see there's image stabilization and image rectification that's done to enable the image of the target to be easily viewed. And the target tracking is done automatically. The user simply clicks on the target, and the system will track the target as the target moves. And as I mentioned, you could have a moving target, or you could simply have something on the ground that you wanted to observe that was fixed in place. Another example of some things we've done is a corridor following approach. We thought this might be of interest to you in the sense that the Panama Canal goes through a mountain corridor. And in this approach, we used some optic flow sensors that we developed here at BYU, and these sensors, we had two of them aimed out the wings, one out the left wing and one out the right wing, and then an additional sensor aimed down at the ground. And the idea with optic flow is, in this particular example, was to balance the optic flow on both sides of the aircraft. The optic flow gives an indication of how quickly things are moving through the image, and if, from our own experience, like riding in a car, things that are very close to us move very quickly. If we look to the side of the car, the things on the side of the road move very quickly through our field of view, and if we look off into the far distance, then things that are far away move very slow. So that's the basic idea behind optic flow, and in this particular research, we wanted to balance the optic flow on both sides of the aircraft. We wanted the imagery to the right and to the left of the aircraft to be moving by the aircraft or moving through the field of view of the sensor at the same speed. And the basic idea is if you balance the optic flow on both sides of the aircraft, then the aircraft will be located in the center of the corridor. So the next slide shows some video from a canyon following experiment that we did here at BYU, where we're using the optic flow sensor to keep the unmanned aircraft balanced or centered in the middle of the canyon. You can see the video stream on the upper right. That is the onboard camera. We also had cameras placed at different locations in the canyon. And here the vehicle is trying to balance the optic flow, and you'll see it's going to go towards this outcropping, and the sensors detect the outcropping and redirect the vehicle to the center of the canyon. This is a location that's about 40 miles from our campus, and this was a fun and exciting experiment for our students. One of the earlier experiments that we did was a cooperative timing experiment, and this is a little cartoon of the experiment. And at the bottom of the screen you see two little triangles. Those are meant to indicate aircraft, and the objective is to get the aircraft to our target location, and that's indicated in yellow at the top of the screen. And we wanted the unmanned aircraft to arrive at the target simultaneously, but on different vectors, and you can see the arrival vectors shown at the target. So the basic idea is that the vehicles plan paths independently to arrive at the target and coordinate with one another in that process. What we wanted to develop was an ability to react to changing conditions and to coordinate the control of the aircraft such that they could respond to these conditions and achieve the objective of arriving at the target simultaneously. And so you can see here a threat has popped up on the right. The vehicles communicate that the fact that a threat has popped up and that there's a change in the plan. They need to replan their estimated time of arrival, and they need to coordinate on how they do that. I won't go into the details, but we developed a significant body of theory that is used for this cooperative control, and I'll just show you some of the results that we obtained. So the idea is that by coordinating with one another, they can plan paths that cause the vehicles to arrive simultaneously while minimizing the exposure of the vehicles to the threats. So here's some video results of some flight tests. You can see initially two vehicles arriving at the same location simultaneously. Then we have three vehicles, again arriving at the target location simultaneously. And this was a great accomplishment, to have 3 vehicles in the air and to have them coordinating with one another. This was one of the more challenging experiments that we've done. You can see here how close the vehicles came to each other from an onboard camera. And then this video shows the telemetry of the aircraft, simply showing where the vehicles were in time. The purpose of showing you some of these things is to just give you a sense of our capabilities and some of the things that we've been able to do. We've done some what we call vision-based precision landing. The idea here is that if you align the line of sight vector from the aircraft, what it sees, to the target, the vector from the aircraft to the target in the vision system, with the flight path, or sorry, you align the flight path with the line of sight vector, then that would cause the vehicle to land on the desired landing point. The challenge is that there's a lot of alignment errors, whether it's due to camera misalignment or biases or errors in the estimation of the attitude of the aircraft, or wind can cause a problem, target motion can cause problems, obviously. These challenges make this problem hard. Conceptually, it's pretty simple, but these challenges that I've mentioned make this a difficult problem. So our initial work, we had a sensor on board, a vision sensor, a camera, that we would have programmed to look for red things. It was looking for red blobs of color in the image, and once those were detected, the control system would direct the aircraft to land on the red object. So you can see a number of trials here where the vehicle identifies the red target in its image, and then using the vision processing board on board the aircraft, and then it directs the aircraft to land on that target. Here you can see a truck, red truck driving along, and then the aircraft coming into the middle of the image here, and again, it's looking for the red thing to land on, and you can see that we're able to do that. And that was another example of a fun and challenging project that has had a lot of success. That technology has been commercialized and licensed. Here's an improved version of the technology where instead of looking for red things, it's looking for features, visual features in the image. This allows the system to be able to track anything that has visually distinct features. And so you can see here the system tracking its target of interest, which is one of the researchers working on the project. I wanted to give you, before I go on, are there any questions? Does anybody have any questions about what I've said so far?
Yes. What is the maximum time of this vehicle to fly without having to recharge again?
So our vehicles can go, the larger aircraft can go for between an hour and a half and 2 hours. That's really the upper limit, and that is with a fairly minimal payload. So if you increase the payload, then the flight time would drop, probably drop to around an hour for a payload of 2 kilograms or so. Okay. But with that said, we use these battery-powered electric aircraft. The technologies we developed are not limited to those aircraft, and we could certainly use a gas-powered aircraft if flight time were a consideration. And also, for simplicity, in the course of doing our research, our aircraft are fairly small. So if we nominally between 3 feet and 6 feet in wingspan. So that makes the aircraft very easy to launch. You can launch them by hand, and you can recover them very easily. The larger the aircraft, the more, once you go over 6 feet or so in wingspan, it becomes harder to launch the aircraft. You can't do it by hand. So if you get bigger than 6 feet, you can have extended flight times, but it becomes it becomes more difficult requires more infrastructure, if you will, in terms of the controlling the aircraft. So that's a long answer. Any other questions? Okay. Let me tell you a little bit about the center, our Center for Unmanned Aircraft Systems. So this center, which we call C-UAS, or the Center for Unmanned Aircraft Systems, is sponsored by the National Science Foundation under their Industry University Cooperative Research Centers program. We receive support both from the National Science Foundation and from our industry participants. We have two universities that are involved, Brigham Young University, and you can see the team of faculty that we have involved in the center here. We also have the University of Colorado as one of our research sites, and we have 4 faculty there that are actively engaged in the work of the center. IUCRC stands for Industry University Cooperative Research Centers program, and this the objective of this program is to bring together university researchers with industry researchers in a collaborative environment to work together on problems having industrial significance. We're interested in exploring new research and development directions for industry, and of solving important problems for industry, and also we're interested in providing training for the next generation of industry leaders in the unmanned aircraft systems area. Certainly the problem of infrastructure monitoring is a new research and development direction for unmanned aircraft and industry, and that's something we're very interested in doing. The IUCRC program has been around for a number of years, for over 30 years. There are currently 61 centers, and by centers I mean groups of researchers working on specific research areas. There's only one center working on unmanned aircraft currently, and we are the designated center for unmanned aircraft. There are over 165 university sites that are currently involved, and over 1,000 industry memberships in the center. So what that means is that there are 1,000, not 1,000 companies, there's probably about 600 companies that have memberships in these IUCRCs. And that just gives you a sense for the scope of industry involvement. This program is well established, it's proven, and it's very successful, and we're happy to be a part of it. The center, our center, is a consortium of organizations with a common research interest, that of unmanned aircraft. A key thing is that the funding that comes from the members is highly leveraged, and I will explain what I mean by that shortly. We have, the members have a shared research portfolio of what we call pre-competitive technologies. This is early phase research, so that the companies, even though they may be competitors, can work together on things of fundamental importance to all of the industry members in the center. The industry members collectively own the research in the center and are involved in the decision making in terms of deciding what projects we work on and helping us define the focus of the research. Here you can see our current membership. We have 2 directorates of the Air Force Research Lab. We have had AAI Textron involved. BP, which is British Petroleum, is a member of our center. Boeing, In Situ, which makes the ScanEagle aircraft. L3 Communications has been a member. We have NASA Dryden involved. NASA Dryden is in charge of the integration of unmanned aircraft systems into the national airspace. The National Oceanic and Atmospheric Administration is very interested in climate and weather, and using unmanned aircraft systems to assist them in their research. Northrop Grumman is a member. United Technologies Research Center, which supports Sikorsky, the helicopter manufacturer, and also Goodrich Aerospace. And then Utopia Compression, which is a small company that does vision or sensing systems for unmanned aircraft. We also have strong interest from the U.S. Bureau of Reclamation and the U.S. Army Corps of Engineers, as well as Lockheed Martin and Raytheon and other companies. In terms of the benefits of being a member, I'll speak quickly to these. I won't go through the slides in detail. But the basic idea with the consortium is that individual members pay an annual membership, and these memberships are pooled. In other words, everybody's memberships go into a pot, and then those resources are used to fund a group of research projects in the center. So currently, a $40,000 membership in the center provides access to over $600,000 in funded research. Another key thing is that university overhead, which is typically about 50%, is waived. So the industry membership fees, all of the money that comes in from industry memberships goes to support the research in the center, primarily to fund the students who do the research in the center. And currently, NSF has provided a strong commitment. For our first 5 years, they've committed about $1.5 million to the research effort. Industry members direct the selection and execution of the research projects. We jointly work with the IAB to conceive the projects, and then the IAB, our Industry Advisory Board, votes to select the projects, and the projects are carried out with their direct oversight. There are opportunities to license the technology generated in the center. All members of the center are entitled to a royalty-free, non-exclusive license to the technology developed in the center. Another great thing about the center is it gives IAB members the opportunity to interact directly with students who are gaining world-class training in the unmanned aircraft systems area, and they have the opportunity to work with them as interns and potentially to hire them as future employees. And then there's a great opportunity to network with other members of the center to establish teaming relationships for research and development, to meet with developers of unmanned aircraft systems platform, and to interact with other end users of the unmanned aircraft systems technology. We have 2 projects ongoing at University of Colorado. The first project involves surveying all of the existing sensor technologies that are suitable for deployment on a small unmanned aircraft system, and compiling a sensor database with extensive information on the different sensing technologies that can be accessed by the IAB members. A second project at the University of Colorado provides for methods for using unmanned aircraft as part of a communication network, whether that's a network that can be set up during loss of traditional communication infrastructure, so an ad hoc communication network. They're also looking at different modes of connecting networks that are geographically not connected. So if you have 2 networks that are far apart and not connected, then they're looking at how they can use unmanned aircraft to carry data between the networks and operate as what they call a data mule, to carry data between geographically or networks that are located far apart geographically. One of the BYU projects is navigation in cluttered terrain with intermittent GPS. I'm showing a video of an aircraft flying down a hallway on our campus, where of course there is no GPS indoors, and this vehicle is navigating using the sensors on board the aircraft. You can see the video feed in the top right. It's using features in the video to navigate, as well as depth or range data coming from the aircraft to detect obstacles and the environment as well. And you can see on the left side of the range map, the obstacles are detected, and shortly here the system will identify, there it goes, they've identified those chairs and tables as obstacles, and then the aircraft is directed to avoid those. Now, this is an indoor experiment, but we're very interested in applying these technologies outdoors as well. Another BYU project is has to do with the operator interface in helping operators of unmanned aircraft to be more effective, minimizing the workload that they have to deal with. A key issue with unmanned aircraft is operator overload. There's simply so many sources of data coming into the operator and so much information to process that sometimes leveraging that information, using that information is very hard to do. Another project is sense and avoid. It's critical for unmanned aircraft to be able to sense and detect other aircraft and then to avoid them. This project involves work to develop a radar that's suitable for unmanned aircraft, small unmanned aircraft, to detect other aircraft, and then the development of avoidance algorithms that would allow the aircraft to avoid each other. And you can see some simulation results depicted in the lower right of some work that we've done demonstrating the avoidance algorithms. On the left side, you also see a radar prototype. This is our connectorized radar prototype. And the next step would be to develop an integrated single board design where these components are integrated on a single printed circuit board. Now, the next area, the area that's probably of most interest to you, is infrastructure monitoring. And I'm going to turn the time over to Kevin to discuss this project and wrap up the presentation.
All right. Well, about a year ago, John and I got together with some other interested collaborators throughout the country, and we started thinking about the potential benefits and uses of applying unmanned aircraft systems to monitoring infrastructure. This is a massive problem in the United States, and I think throughout the world, because more and more we are interested in infrastructure that is resilient, meaning that it can endure more hardships and serve for a longer period of time than perhaps it may have been designed to. And one of the key components to having a resilient infrastructure is the ability to monitor it, and when small problems arise, to be able to repair them before they turn into large problems. So we were interested in investigating new ways that UAVs and various sensor types could achieve specific research objectives related to the monitoring of modern infrastructure. So a few ideas, for instance, would be automatically collecting data from different types of infrastructure, monitor and process that data, and then identify anomalies and automatically relay that information to personnel that would need to respond and perhaps mitigate or repair that anomaly. We were interested in using UAVs to enter infrastructure environments that may not be feasible or safe for real people to go. An example of that might be an area of rockfall or of severe slope instability where you may not want to send your geologist or your field engineer, but be able to send a UAV to gather that data that may drastically improve safety. Of course, we geotechnical engineers, we all share a common interest that we would like to do things better but for a cheaper cost. And certainly, I think using UAVs has the potential to reduce costs drastically, but at the same time improve the quality of the data that we obtain. And then I'm also interested in, once we have the data, what do we do with it? I'm interested in developing better modeling techniques with this richer set of data that we can obtain from unmanned aircraft and other methods of remote sensing. So with these guiding principles, John and I set off and we teamed with Tim and the C-UAS to initiate this new research thrust, and it was initiated earlier this year. Go ahead, Tim, and switch the slide, please.
Oh, sorry. Not sure what happened there.
That's okay. I like those slides.
Oh, boy. I seem to... There we go. Sorry.
There we go. Excellent. So during the past year, here in 2013, we have approached several of the both the existing members of the C-UAS as well as potential future members of the C-UAS on this issue of infrastructure monitoring. And as we suspected, several members and several organizations have extreme interest. They're very interested in this topic, some more than others. Some companies like British Petroleum, who have countless dollars tied into infrastructure related to their various platforms and pipelines, they're extremely interested in this. Other current members such as NASA and the National Oceanic and Atmospheric Administration, NOAA, they're interested as well. We have approached recently the U.S. Bureau of Reclamation. I'm sure that you gentlemen know that the Bureau of Reclamation oversees and administers all of the major dams in the United States. And they're extremely interested in this topic and using UAVs to help monitor and inspect their dam structures and their canals. Other organizations that we have approached and have spoken with include other oil companies such as ConocoPhillips, Shell, ExxonMobil. A few of those companies have expressed interest. We've spoken with Alyeska. They are the company that owns and maintains the Alyeska pipeline, the large oil and gas pipeline from Alaska down to the United States. We've opened a dialogue with the U.S. Geological Survey. They've expressed some interest, but more interested were the U.S. Army Corps of Engineers, and it's in fact through the U.S. Army Corps of Engineers that we began speaking with you at the PCA through my good friend Bill Marcuson recommended that we initiate a dialogue. But the Army Corps of Engineers is extremely interested in this topic because using UAVs could drastically improve the way that levees are inspected and monitored in the United States. Do you have any questions up to this point?
No so far.
Okay. Tim, next slide, please. Excellent. So, earlier this year, the U.S. Bureau of Reclamation wanted to do a little pilot study just to investigate the potential benefit of using unmanned aircraft to monitor their dams. So they provided us with a small amount of money to pay for student wages and gave us some access to some sites here in the state of Utah, and said we would like you to take UAVs and just regular cameras, just a regular optical sensor, to these different sites and develop computer vision models of these sites. We want to see what is possible. And so that really was our main objective. The 4 sites that they gave to us, the first site is called the Arthur Watkins Dam. It's in northern Utah, and it constitutes one of the longest dams in the United States. It's actually a fully enclosed reservoir. The dam encircles the reservoir, and because it encircles the entire reservoir, it is approximately 14 miles long. The second site was a smaller reservoir, Huntington Reservoir. And then there's a long canal connected to this reservoir. They wanted to see what kinds of models we could get from this canal. And then the fourth site was a large dam known as Joe's Valley Reservoir Dam. And they wanted to see what a computer vision model of a large dam would look like. So our main goals were to demonstrate the potential usefulness of computer vision models to the Bureau of Reclamation, to develop and initiate a database of point cloud models that we could use to test and improve and validate future computer vision research, and then for our benefit to create a benchmark or a baseline for our own UAV computer vision research. Tim, next slide. So the platforms that we chose to use for this summer research are shown here. The top platform is a fixed wing that 81 inches wide, so that's a little over 6 feet. The fun thing about this platform is that our students constructed it on their own and made their own modifications. And it's an excellent platform, and it flies very, very steady, even in very stiff winds. We have flown it in winds exceeding 45 miles per hour, and it flies very smoothly and very steady. We've affectionately named this platform Big Bird. I don't know if they have the television show Sesame Street in Panama, but that's what we've named this UAV. The second UAV is a smaller, it's a 6-foot wingspan, but this UAV was special because it was outfitted with the Procerus autopilot, or I'm sorry, the Kestrel autopilot. So we were interested in just experimenting with the ability of the UAV to fly itself if we gave it a predetermined path to fly. The sensors that we were using, shown in the bottom of the screen, we were using a GoPro Hero 3 camera. These cameras are very popular today with sports enthusiasts who want to film their adventures, either skiing or kayaking or whatever. And so we used this camera. And then on the Procerus platform, there is a more complex gimbaled Sony camera that has a lower resolution, but it has the ability to rotate and be able to focus and move and look at different angles. So these are the two platforms that we used for that summer research. Tim, next slide, please. So I'd like to show just some results of some of the models that we were able to develop. And we're also going to be switching screens, and I'll show you some of the actual 3D models of some of the sites as well. Coulter, remind me again which model you have up on your screen.
I have the Huntington Lake model up right now.
Okay, great. I'll let you show that when we talk about that. So this first model, gentlemen, shows the Arthur Watkins Dam, the very long dam. Jaime, you asked earlier about flight time. With the small UAVs that we were flying, we on a single battery, we were able to fly for about 15 minutes. In those 15 minutes, we were able to fly about 7 miles of the dam, so about half of the dam. And using the images that we collected from that flight, we were able to create this three-dimensional model of the dam itself. This was one of our earliest models that we developed. It's somewhat unrefined a little bit, but certainly we were able to see the dam. We were able to see the top of the dam and the tire tracks. We were able to see individual boulders and rocks. And I would say the resolution of the model that we developed was on the order of about 1 foot to 1.5 feet. But the model was heavily distorted because the GoPro camera does not have a flat lens, but it has a curved lens known as a fisheye lens that allows you to get more light into the lens. As a result, our models were curved and weren't flat like we'd like them to be. So that was an interesting learning experience. The next slide, Tim. The next site was the Huntington North Reservoir. This was interesting because it's a very small reservoir, but it is very asymmetric. In other words, it's very curvy. The dam itself is about 74 feet high, and we were able to fly the dam and model it. To gather the images needed to create this model, we had our aircraft in the air for just a couple of minutes. That's all the images that we needed to create the model. We were able to fly about 0.6 miles of the dam crest before we decided to land and bring the model or the aircraft back home. There were several tourists playing in the dam, and for safety reasons we wanted to keep our aircraft away from them. This is a screenshot from the canal that we were able to fly, and this was a very interesting experiment for us. We were interested in seeing what kinds of details we could see from the canal. The canal itself is very small. It's only about 25 feet wide. It was much, much smaller than the canal that you deal with every day. We were able to fly and model 2 different sections of the canal. One we did with our automated UAV, and the second one we did with our radio-controlled UAV. And we, because this is just preliminary and experimental, we only flew about 1/2 mile of the canal. The other one was longer, and we flew about 1 mile of it, and that one was completely automated. But we had some interesting experiments that we wanted to run. Tim, could you go to the next slide?
One second.
Okay.
There we go.
So you can see in the bottom pictures that we had all of our vehicles there at the canal, and we wanted to see what would happen, how the different models would be if we moved the vehicles. So in our first flight, we had all of our cars and our vehicles parked on a road further away from the canal. And then on the second flight, we moved some of our vehicles right next to the canal. And the other vehicles we left where they were parked previously. What we did then was, with our computer vision models, our point cloud models, we performed a change detection analysis. We wanted to see if we would be able to detect significant changes. The top picture shows the results of that change detection analysis. The points that are colored green indicate that change was detected between the 2 computer vision models. And the smaller group of green dots indicates a white truck that we moved next to the canal. And then the larger set of green dots was my Suburban that I moved close to the canal. And so you can see that it did indeed detect those changes. Further over to the right, where it says blue truck and trailer, you notice that those dots are not colored green because we did not move those vehicles. Therefore, no change was indeed detected. Therefore, we are excited about this concept of change detection, and I think it has very some useful practical implications and applications in infrastructure monitoring, to be able to detect significant changes or movements that otherwise you may not be able to detect unless you had an instrument installed there. Next slide. Okay, and this was the fourth site. This was the large dam, Joe's Valley Reservoir Dam. Though I don't know why it says it's a canal with 25 feet wide. That might be an error there.
I think that's 250. Yeah, I think that was from the canal slide. This one, yeah. I think is.
I don't know why that's showing there. Interesting. So anyway, the dam itself is very long. It's several hundred feet long, and it is over 100 feet high, and it impounds a large reservoir. So on this particular day, the wind was blowing about 45 miles per hour through that canyon. We were unsure how our aircraft would perform, and it performed wonderfully. All of those little dots that you see, those little triangles, represent locations where the camera images were taken from our UAV. So you can see the flight path of the UAV. We had the UAV in the air for less than 5 minutes, and with that set of images that we collected, we were able to develop a full three-dimensional model of not only the dam, but the entire surrounding canyon. So if you would like to, again, give me control, I will pull up the actual three-dimensional model and pan around so that you can see that. Let me bring this. Yes.
Yes. What was the line separation between the fly lines? The distance between the fly lines?
Oh, the height of the UAV, the altitude?
No, not the altitude. The distance horizontally between the fly lines, in order to cover the, to generate the 3D points.
So Kevin, how far away were the flight lines? Because I think that dam is about, is it 250 meters, or was it feet wide on the top?
It's meters wide.
Okay, so the width of the dam there is 250 meters, and so you can see that we had multiple passes about every 30 meters or so.
Okay.
Yeah, I apologize. I did not understand the question there, but that's correct. So all we did was we just flew our UAV back and forth over this dam, and then used those collections of images. But so you can see that as I flip this model around, that it is a very comprehensive model. You can see everything from the road to our vehicles that were parked there, to the trees. One thing that was of particular interest to us, and that the Bureau of Reclamation was interested in, is this region where my pointer is moving is a landslide that occurred about 30 years ago right at the toe of the dam. And they were interested in seeing how we would be able to detect or show the landslide, and indeed, we were able to see the landslide rather clearly. The landslide is no longer active, and so there's still some vegetation starting to grow, but you can see that we were able to model that pretty well. So these images we were able to collect in less than 5 minutes, and in less than 1 day we had processed those images and created this model. Now, some things that I would like to show and point out that make this technology very exciting. If you look at the side of the canyon wall here, sometimes flying these things is a little challenging. There we go. So if you look at the size of those canyon walls, you can see that we can model underneath overhangs and rocks, where if I was relying solely upon aerial imagery, this is what I would see. I'd see the top of the rock, but I would not be able to see it beneath it, or, and get an idea of what that looked like underneath. And this is significant, particularly if you're in areas of rocky terrain that's very uneven. And I thought certainly that was really neat to be able to see that. I was completely blown away by the detail that we were able to obtain from this model. And we've improved even from the time that we've developed this model. We're now using better cameras, better processing techniques. I'm confident that if we were to go back out to this site again, we could produce a model that looked even better than this at this point. So my excitement is, now that I have a model like this, what kinds of exciting things could I do with this model? In terms of writing algorithms, maybe to say, I want to detect any sorts of movements related to this landslide. So using change detection algorithms, saying if I see any sort of movement, I want to be notified what those movements are and warned. Maybe detecting potential changes in seepage on the back side of this dam, looking for changes on color. All sorts of different applications that we could possibly do here. So this is just, again, an example of this model. Do you have any questions on this model or what we did at Jones Valley Reservoir?
So far.
Okay.
I have a question.
Okay.
We can see that in the model that you have no grass, no trees in the area. Here in the canal, we have a lot of trees and vegetation that probably can, we cannot see the land itself. So I know that I understand the model. We can see the 3D image very good, but here in the canal we are using a technique to detect the topography, but we have to make some adjustments for because of the vegetation.
With LiDAR.
With LiDAR.
Yes.
Right. The LiDAR technology. So more than a question, is a comment. So we can see that this is like a desert. It's arid. The area is arid, no vegetation, but in the Panama Canal, there's a lot of vegetation that we have to fight with in order to have a good model for the terrain model. So
that's right.
That's more a comment than a question.
Right, and we understand. And in speaking with the U.S. Army Corps of Engineers, in areas of the United States like Mississippi where they have levees, they have a very similar problem. Very heavy vegetation. You cannot see the ground from the air directly using optical methods. And so that is a very interesting and exciting research challenge, and one that we would be happy to address and look at. Now, I know that LiDAR technology is commonly used to, in essence, see through vegetation, and that shows a lot of promise. There are some limitations to LiDAR that computer vision could really improve. And so one of the research goals that we have is to be able to combine LiDAR with computer vision to take advantage of the benefits and advantages of LiDAR, but at the same time take advantage of the benefits and advantages of computer vision and combine the two to develop what I would call a super model. And maybe one that would be able to go through the vegetation if you wanted to, but be able to add the rich detail from the photographic images that you may not be able to capture with the LiDAR. So we are in the process of acquiring a small LiDAR unit that we could mount on these small UAVs. We're extremely excited about that. I know that traditionally in our field of practice, if you wanted to use LiDAR, you had to charter a full-size aircraft, and that can be a very expensive endeavor. I think the potential benefit of using a small unmanned aircraft with LiDAR mounted to it, you could potentially save a lot of money in terms of fuel costs, or in terms of hiring pilots and chartering a full plane, but still get the same amount of rich data. And so that is the direction that we're hoping to go.
Kevin, I know you're aware of this. I would also mention that there may be possibilities to leverage radar as a sensor, and that BYU is very well known for their work in radar. And so, as you indicated, we have the possibility of optical or laser-based sensors, but also radar to come up with a multispectral model or image of the terrain. So I would just suggest that as a possibility as well.
Absolutely. I say that the radar has already been demonstrated to be able to detect changes and movements in ground as small as a few millimeters, and to do so very reliably and accurately. And so that has tremendous potential. Thanks for adding that, Tim. John, let's go back to the presentation on Tim's computer, and we'll wrap up.
Okay.
We'll go to the next slide, Tim.
1 second. There we go.
Okay. So, gentlemen, one of our current research interests that we're working on right now is to really refine computer vision models. And this is, of course, in preparation for being able to combine these models with other rich data sets like LiDAR or radar. Currently, the best that we can find in literature in terms of resolution for computer vision is on the order of about, well, what we're achieving, 12 inches to 18 inches resolution. We want to achieve sub-centimeter accuracy with our models. And we know this is possible because we have seen it with our handheld cameras. So the models that we're showing right now are on the left a geotechnical lateral pile load test performed by Dr. Kyle Rollins, a colleague of mine at BYU. And we got very good resolution on this model, certainly sub-inch, I would say approaching centimeter accuracy. And then another model that we performed on a rock fall near Salt Lake City. This is a boulder from the rock fall. Using just 50 images, we were able to get very close to sub-centimeter resolution on this model as well. So in order to achieve this, we have to use better cameras and better image control. And we're currently experimenting with merging different types of computer vision as well as inertial correction, so tracking the movement of the UAV in order to obtain these very, very fine resolution models. Now again, these models do nothing to see through vegetation, but certainly for certain applications they could be very, very beneficial. Next slide. To demonstrate how using a different UAV can improve a model, I have a comparison here. What we have is a spillway that is maybe 30 feet in length for a small little retention dam close to Provo, Utah. We flew over this dam using two different UAVs. The model on the left was using our fixed-wing Big Bird UAV. It was flying at an elevation of about 200 feet above the dam at a speed or a velocity of about 40 miles per hour. And you can see that in general, you can see the dam, you can see the shape of it, and get an idea of what's there. The model on the right we used with the quad rotor UAV that we currently own. An image of that quad rotor is shown at the bottom of the screen. This quad rotor was flying at about a 50-foot elevation above the dam, or the spillway, and it was flying at velocities less than 15 miles per hour. You can see that the model that was produced on the right is visibly better than the model that was produced on the left. Both of those platforms were using the same camera, but just the way that we changed the flight, the way that we changed the platform really had an impact on the quality of the model. Next slide, Tim. And John, if there's anything you want to add, feel free to jump in as well.
Sure. Okay.
So I sat and I thought for a little bit, and I thought of some ways in which some UAV research might be of interest to you at the Panama Canal Authority. For instance, using computer vision, and I'm going to add LiDAR and radar to that, to detect various canal anomalies, things like significant slope deformations, excessive erosion, seepage, sand boils, whatever it is that you are interested in monitoring and detecting, using these technologies and sensors to try to improve the way that you can detect those. Another would be combining other sensors with computer vision to improve our detection capabilities. So like Tim was saying, can we combine various sensors onto one platform to create a multispectral model that is a much richer data set and much more realistic and accurate, and that can detect anomalies with a much better success rate? And then finally, looking at the challenge of automation in monitoring the canal. So all of the research that Tim spoke about at the beginning of the presentation, all of that is very applicable and necessary when you want to start applying UAVs in the real world. And so how in the world could we get a UAV to monitor the canal in an automated fashion? So being able to fly and guide the UAV in a tight canal environment. How can we transfer the data from the flying UAV or the UAV after its flight into the system and analyze and process that data? And can we improve UAVs and build brand new UAVs that are uniquely designed to meet the objectives and the needs of monitoring a large canal like the Panama Canal? So all of these are very interesting research questions that I think would potentially benefit you at the Panama Canal Authority. Anything that you want to add up to that, John?
No, that's exactly, I think, a very good statement of where we want to go with infrastructure monitoring, and in particular combining, like you mentioned, the LiDAR and these other sensors to specifically detect anomalies and or deviations. And as you put in the last bullet there, I think that's absolutely right, that we want to automate these as well to be able to get better computer vision models and also facilitate regular monitoring of these canals, dams, levees, the infrastructure that we're interested in addressing. So I think that's a very good summary slide of where we're going